Hi everyone. So today I'm going to talk about smart chargers, and we're going to try to determine whether smart also means secure or not. I'm Aymeric Palhière. I work at Synactive in the reverse engineering team. And let's start by introducing a few concepts. So I'm pretty sure you've already seen smart chargers. It looks like that. Sometimes it's hidden inside a bigger box, but it's basically the same device. It allows you to charge your car faster, but it comes with a lot of smart features like a remote access, the ability to handle billing for multiple users. And what's interesting is that it can be installed at home or in public places such as a gas station or your workplace. Just a few diagrams to make the presentation look a bit smarter than it is. We see a lot of electric car. It's a booming market. And if we have more cars, we need more chargers to charge them. So there are already millions of them, and that's already enough to make it an interesting target for an attacker. But why would I want to compromise a charging station? Well, first, I could want to charge my car for free. It's already interesting, even though it asks a bit of technical investment in order to do that. I could also want to trap a charging station, either to steal banking information from other users or to add it to my botnet. But in my opinion, the most interesting scenario is to pivot within a local network the charger is connected to. Either it is a residential one or a corporate one. The real context of this study was to take part in Pontoon. It's a contest where you have to demonstrate your ability to compromise some devices, and if you succeed on stage, you have 3 attempts, you earn money. So it's very interesting. And what's even more interesting is that back in 2024, was the first edition of Pontoon Automotive, which is dedicated to chargers. There was a Tesla, some IVIs, etc. And generic rules about Pontoon is that newcomers are generally easier targets because they've almost never been audited. The agenda for this talk is the following. First, I'll describe the architecture of the chargers, how they work, how they interact with other systems. Then we'll try to identify different attack vectors and assess the security level of these devices by analyzing the different vulnerability we found for Pontoon and their exploits. And finally, because we're some good guys, we'll provide some recommendations for improvement. Okay, first, what's a charging station? Well, here are the models we've studied. They all basically look the same. You have a big box and a Type 2 connector that will be plugged to the car. So we have also studied those one, and finally the ubiquity one. But what's inside the box? First, on the left, there's a power board. Well, there are some impressive electrical components. I don't know much. It's not really relevant to us since it's only used to deal with the power and talk with the car. But on top of that, we have the main board. It will hold all the communication interfaces. You see first a Bluetooth module, for example, some RAM, and on the other side there are some a flash memory, RJ45 connector, and even sometimes there are some 4G. So that's a lot of connectivity, and that's pretty interesting for an attacker. You see what's in the box. It's always the first step when you want to start looking for vulnerabilities in such devices. You have to open it and find a way to obtain the firmware so that you can look for bugs. In some cases, this firmware were available online freely, and that's really useful for us, but sometimes they were not. And we had to use a physical attack to obtain it. You see, for example, there are some test points. I don't know if you see there are some test points here, stuff like that. That's what you're looking for. and sometimes it's JTAG, sometimes it's SWD. These are protocols that will allow you to dump the content of the memory and obtain the firmware this way. So that's what we did for some. Okay, I'll introduce a few concepts that will help you understand the rest of the presentation. That's the charging port, also called the Type 2 connector. There are some basic electronical stuff. You have a neutral and line 1, 2, 3 to transmit power. You have an earth or a ground, and you have also two interesting lines for us. The proximity pilot, which indicates a cable is present, and a current rating. And the most interesting one is the control pilot. It's a pulse width modulation signal, which sends basic information between the car and the charger. For example, the maximum current available, if the vehicle is present, if it's currently charging, etc. On top of this line, the PLC signal is superimposed. So those two signals are superimposed and they don't use the same frequencies. So you can have both at the same time. And this one enables smarter communication. It's actually what lies under V2G and plug-and-charge protocols. Speaking of V2G, for vehicle to grid, it's actually a stack of standards that allows interacting with the grid, which is the electrical network. That way, electric vehicles can draw energy from the grid, it's called charging, but they can also send back energy, discharging. What's interesting here is the link between the charger and the backend, which is made by the OCPP protocol. The OCPP protocol is an open communication standard to discuss between the charger and the backend, and it's generally used to remotely manage the charger. The protocol is pretty simple. You have an example payload on the right. It's basically some JSON over a WebSocket connection over internet. So it's pretty trivial, but it allows to do really interesting stuff, such as monitoring the charger, updating its firmware, starting or stopping charging sessions, etc. It supports basic security features such as certificate authentication, TLS, and the ability to sign messages. We'll come back to it a bit later. To sum up the interconnections between the charger and different systems, I've done this simple diagram. You see there are lots of interfaces. The big gray square is the charger, and it interacts with the car to send basic information and to send power, but it also interacts with its backend. Another key concept is the strong design constraints you face when you try to design an IoT device like that. You want something cheap, so you want a cheap MCU, but the problem is that cheap MCU don't have important features such as an MMU for memory management unit. This is what allows you to isolate processes, have some memory regions with permissions, and implement basic concepts such as virtual memory. If you don't have that, you can't have important security mitigation such as ASLR, for example. And in most of the chargers, we've met MCUs belonging to the first part, the cheap one. Sometimes we found higher-end MCUs, including a memory protection unit. It's better, but it's not the best. And finally, there are some high-end SOC that we've never seen, who have a real MMU capable of running an operating system such as Linux or Android. Okay, now you know what's a charger, how it works basically. Let's see how secure it is. If you had to design a security model for your charger, here is basically what you want. First, you don't want the charger to explode once you plug it to a car, so that's safety. It seems logical. Then you want your users to be authenticated when they want to charge. You also want to protect the data they store in the charger, such as banking information. And finally, you don't want the charger to be jailbroken and run arbitrary code or Doom. Okay, so that's the basic security model. But how is it applied now? Once you have the security model, you have to study the attack surface. If I try to sum up everything we've seen, the first one is the cloud backend. It holds sensitive information, and you can also administrate the charger from the cloud. So it's pretty sensitive in terms of security. You also have sometimes a mobile application, which allows you to update the firmware of the charger or to send Bluetooth commands. You'll see later, it's very interesting. Often you also have some Wi-Fi or Ethernet connectivity on the charger. So that means that someone on the same network could reach some network services exposed by the charger. There are also user interfaces. On some of them you can pay using an NFC card or authenticate. And there are also USB ports sometimes. And finally, you have the charging port, where you can discuss the car with the charger by the charging port using the CP line. Finally, there's the physical layer, but we've used it to obtain the firmware and debugging setup, but it was not allowed as a valid scenario during Pwn2Own, so we removed it. If I come back to my diagram, you see that actually most of it is an attack surface. And in the next part, I'll try to show you how we've attacked all of these surfaces, basically. Well, let's start by the USB surface for the Hotel Maxi charger. First, there was a USB port hidden behind a piece of plastic, but if you had a screwdriver, you could open it, so it's fine. It was approved by Pwn2Own organizers, so we considered it a valid scenario, and we started looking for bugs in the USB stack. You see the function is the function handling setup packets. In the USB protocol, setup packets allow to initiate a transfer, and they indicate the size of the data that come after. Here, the packet variable is completely controlled by the attacker, and you see the size, W length, is not checked, only it must be different than 0. So this function gives two strong primitives. Also the USB setup buff is a fixed size 16 bytes, I think, heap buffer. So if you give a bigger size, you have either an out-of-bound read, or an out-of-bound write, depending on the direction of the packets. The idea here is not to focus on the exploits, but just to show you the vulnerability if there were any memory protections or not. In that case, there were none. So what we did is that we wrote a shellcode and patched, using only this primitive, patch a function pointer on the heap to jump on our shellcode, and that was done. Because there were no security mitigations. Otherwise, it would have been much more difficult. Let's talk Bluetooth now. Still on the hotel, but a year before. We could send Bluetooth commands of the following form. There were two fields, OP code and func code, allowing to dispatch our packet through different handlers. However, all functions require authentication. Let's see how this authentication is made. Well, actually, there are two ways to authenticate. One is good, and the other is worse. The first one uses a magic key, which is derivative with the password, etc. It's fine. But the other one, which has BD in its name, for backdoor maybe, only uses an hard-coded constructor key. So if you are able to reverse engineering this binary, you have the key. Okay, fine. Now we are authenticated. We can reach more code. And here you see the dispatcher between different commands. And we've read the code basically, and focusing on this one, charging control param. Well, the function is really trivial, but we see a fixed length buffer on the stack, a memcopy in this buffer with controlled contents, no size checks, smells good. Well, that's enough. The stack is executable. There's no particular mitigations. The only problem is that we're facing a real-time operating system, so we won't be able to have a real shell. But it doesn't matter because at Ponsuon you only have to show that you can run code. And a way of making this is, for example, blinking the LEDs in the front panel of the charger. So we did a short rope chain that was jumping to a shellcode on the stack, and the shellcode was blinking the LEDs. Still no security mitigations. Another Bluetooth vulnerability on another charger, the ChargePoint on Flex. This one was even more trivial, I would say. The device broadcasts two BLE characteristics, ESSID and password. That means anyone unauthenticated could write this characteristic and change the SSID and password of the ChargePoint. Then you have two binaries. One onboardee receives the BLE packets and forwards them to WLAN app via IPC. And the second one handles the Wi-Fi configuration message. You reach this function, finally, when you write the Wi-Fi password characteristics. BLE controlled variable is actually controlled. So here you have at least a command injection. It's because you control the BLE, it's injected into the command, and the command is executed by the popen function, which is dangerous. So pretty trivial. Here is the exploit. I think we missed 2 lines, but that's it. You connect to the device, read its characteristic, write a new password, injecting a Linux command. What's really useful to us is that the telnet binary is present on the system, so you have an embedded reverse shell. It's cool. And that's it. One point about mitigations, such vulnerabilities are pretty difficult to mitigate, but they are relatively easy to prevent if you simply audit the code and look for dangerous functions such as popen or system or whatever. Another attack surface we've targeted is the link between the charger and the backend. So it's using OCPP, as I've explained previously. The binary responsible for that on the ChargePoint is the CPS relay, and while browsing the file system, we found the cps.conf configuration file. It was pretty interesting because we saw some paths related with certificates, because the connection is, the WebSocket connection is protected by TLS, so we need certificates. And we also saw a variable, verify hostname equal 1. Our idea here is to intercept the connection and to man in the middle. So we have to authenticate. But this variable verify hostname, well, we're like, oh, it will be difficult. But actually, this variable is corresponds to a curl option that's very misleading. Because back in the older curl versions, when you set this variable to 1, it actually means, okay, the certificate must be signed by a trusted CA, but don't check the domain. So don't verify the hostname. If you want to also verify the hostname, you had to set 2. It was so misleading that it has been fixed in the recent versions of libcurl, but this one was outdated. So okay, why not? Also on the file system, we found a certificate signed by the ChargePoint CA, which is good. Not for the right name. The name actually is the one, the charger one, and we wanted to impersonate the backend. But since we have this curl option, he doesn't care about the name. So that's fine. Using this, we can impersonate the server and man in the middle the connection. That was also protected by a client certificate, but we found it on the file system, no problem. The most difficult part was probably to configure burpsuit to being able to intercept the communication, but we finally managed to do it. And then we were able to see all the OCPP commands passing between the backend and the charger to modify them and to send them. So that unlocks a whole a new attack surface. You have an example of an OCPP command on the bottom, and you see it's just JSON, but there's a custom format here. That's a command only on the charge point. The first field, the fields are separated by bytes, and the first field is the command name, and the rest are arguments. So now we can look for vulnerabilities in the OCPP commands parsing. Well, let's take first handler randomly. Oh, there's a vulnerability. You see there's a while loop. It parses arguments for the command. And while it finds some new arguments, it copies them into a stack buffer, a fixed size. Well, if you send enough arguments, you have a stack buffer overflow. There's almost no mitigations except the NX bit. It means the stack's not executable. So we had to build a simple rope shell calling a system and our favorite binary telnet D. And that's it. So it's a bit better, but still not perfect. A very original one, attacking the charging ports on the Tesla charger. Here is a capture of the control pilot signal. You remember this line in the Type 2 connector? And actually, on top of that, Tesla implemented a single wire protocol. A single wire CAN protocol, sorry. On top of CAN, if you know a bit, there can be UDS, which stands for Unified Diagnostic Services. It's a protocol that allows operations such as updating a firmware, for example. Often UDS sessions are authenticated, but in that case, the authentication was only a single byte XOR on a not coded value, so not too difficult. And UDS also can be used to obtain Wi-Fi AP credentials. The final information to understand the exploit is that on an older version of the Tesla charger firmware, there was a debug TCP shell reachable via Wi-Fi. Now you have all the key parts. What's the plan? We want to downgrade the charger's firmware to the older version using UDS. Then we want to obtain the AP credentials. We connect to the AP, and then we can reach the TCP debug shell. However, it was not a full shell, so we had one more step to be able to execute arbitrary command. But this shell was very old, full of vulnerabilities, so you take any command of the shell and there's a vulnerability, so it was not the most difficult part. What was really interesting about this one is that you have to fake a car to discuss with the charger. And in order to do that, my colleague David built this box, which is actually a Tesla. And I highly encourage you to read his blog post. It's very fun. There were stack cookies, but there was no anti-downgrade mechanism that would have completely killed the exploit and not the rest of the mitigations. Let's attack the local area network now on the Juicebox 40. Well, this one runs Gecko OS. Maybe you've already heard of that. It's well known and documented, but it comes with a remote terminal enabled and listening on TCP port 2000. There's no password by default, and you can't disable it. So, fine. Let's explore the documentation. There are lots of commands available. One is HTTP download, and reading the documentation, you see that it contains a documented format string vulnerability. I don't really know why, but if you send this command, it leaks some heap addresses. Okay, why not? Let's use it. But it's not enough to compromise the charger. We need to find something more. While reading more code, in this function we found a buffer overflow, because when you send at t, 23 bytes are copied to a fixed size stack buffers. So if you do it enough times, there will be a stack overflow. Okay, now we should be able to combine these vulnerabilities in order to get code execution on the device. First, we use the format string to leak some heap addresses where we'll be able to store our shellcode. And then we'll use the Stack Overflow to redirect the execution flow to our shellcode that we know the address. And finally, we trigger the exploit by calling HTTP download command. It was a bit more complicated, but still doable without mitigations. There's more, actually. I don't have time to talk about that today, but the one on ubiquity was pretty interesting because there were mitigations, but we found a logic flow that completely bypassed them, so it's a bit sad. And another participant attacked the 4G on charge point, so they decided to remove completely the surface this year, which is a good idea. Let's take a step back and analyze the results of this study. Well, we clearly see that security was not a priority while designing these EV chargers. We don't have all the main mitigations, I would say, which are more than 20 years old, and the code has not been audited clearly because you have some command injections, you have some trivial vulnerabilities. An audit would prevent that. There are a lot of connectivity, a lot of protocols, and that means a wide attack surface. Do you really need to have all these communication methods on a charger, like 4G, for example? Is it all necessary? The good point is that initiatives like Pontoon, they slowly but surely help raising the security level of this industry, because it can be seen as a semi-rigorous audit. There are multiple persons auditing all the code every year and reporting vulnerabilities. Also, the good part is that the new edition of Pontoon has just been announced. There are still EV chargers and there are newcomers, so maybe stay tuned. Finally, some areas for improvements if you ever have to design a charger. Well, first you want to harden the system. And it starts at the design stage, when you have to think what MCU will I use for this device. The cheaper won't be the best. When available, you should enable security mitigations and, of course, audit sensitive code. There are really some quick wins, such as avoiding dangerous functions, a p-open system, etc. And once everything is hardened, you can try to reduce the surface. For example, disable useless service, debug shells, etc. It's not really needed, but it's a second step. If you want to know more about this, it's detailed on Synactive blog post, also other resources that were very interesting. And I'd like to thank, of course, my colleagues who worked with me on this project, and it was really always fun to work on such targets. And that's it for me. If you have questions.
We have time for one or two questions.
Hello. I have a question. What was the attack pattern that you used in order to dump the different firmwares of the different chargers that you had to attack? Because as you said, the most security measures were about hiding the firmware. So what was your strategy in order to dump them? Thank you.
So I'm not sure I've heard all the question, but you ask how did we obtain the firmwares, basically, yeah. So in some cases, they were available online or in a public SDK, so that was easy. And on some cases, in the hardware part, I'll try to come back to it. It's a bit. There were some JTAG connectors or SWD connectors on the board, and we, yeah, for example. Yeah, here. Here, it's, I think, SWD connector. You can plug to it and dump the content of the memory. So it contains the firmware. And sometimes use other protocols such as JTAG, etc. But there are ways to dump the firmware when you have a physical access. This can be protected also. There are protections such as the RDP, etc., but it can also be bypassed in certain cases. Advanced people, and I'm not one of them, you could also desolder the flash and read its content, but it's getting a bit too sophisticated for me.
We have time.
Hello. Yes, I wanted to know, you mentioned that one of the firmware was encrypted, but was it signed, and how many of the EV charger had the secure boot mechanism?
No, none of the chargers had secure boot implemented. The encrypted one was downloaded by the companion app and uploaded to the firmware, which was able to decrypt it. We were a bit lucky on this one. We used some cryptography skills to guess the encryption method. It was a bit difficult, but we using solvers such as Z3 and really some beanwalk and some it was I have another presentation about that. It was a bit difficult, but we managed to recover the plaintext firmware without only guessing the crypto.
Thank you.
Okay, let's thank our speaker again.